So I'm going to give a talk on one-way communication complexity of partial XOR functions, and it's based on work with Vladimir Podolsky. So the plan of the talk is following. First, I will describe problem and the motivation. Then I will go through our results, and then I will outline some of our proof ideas. And we study functions defined on Boolean cube. We often consider Boolean vectors in the Boolean vectors as a linear space of a field of two elements. And we denote the bitwise addition of a field of two elements with plus sign. We study XOR functions, that is, functions of two arguments which are Boolean strings, and these functions can be expressed as some function of a XOR of its arguments. One such function is equality, that is a function which takes two arguments and is equal to 1 if the arguments are bitwise equal, and it can be expressed as a XOR function. It can be expressed as a conjunction of negation of XOR of input bits. There are several reasons to study XOR functions. First of all, there are just several interesting functions that belong to that class, like equality, functions based on Hamming, distance, and this includes gap Hamming problem. Also, Fourier analysis works well with XOR functions. And also, the reason to study XOR functions is a log-rank conjecture. We name a matrix of size 2 to the power of n times 2 to the power of n, a communication matrix of function f, if in the kel ij, it's written the value of f on the strings I and j. It's known that communication complexity is lower bound with a logarithm of rank of communication matrix, and there exists a polynomial upper bound. So the question is if there exists a logarithmic upper bound. And for XOR functions, we can apply Fourier analysis. We name Fourier sparsity of a function number of its non-zero Fourier coefficients. And for XOR functions, rank of communication matrix is equal to Fourier sparsity. Now I'm going to introduce several models. First is communication complexity. In general case, Alice holds one of inputs x, Bob holds the other input y, and they communicate to compare the function. In one-way case, only Alice can send the message to Bob, and then Bob have to name the answer. For example, we can consider composition of index and XOR functions. That is, Alice has two strings x and x prime of length 2 to the power of n and n. Bob has strings y and y prime, and they XOR the strings correspondingly, and they want to find the bit of x plus y at the position x prime times plus y prime. And there exists a two-way protocol. Alice sends Bob x prime, Bob sends Alice y prime. Now they both can compute the position x prime plus y prime, and Alice sends bit of x at position x prime plus y prime. Bob computes his bit at the same position and source it with Alice bit to get the answer. So the protocol takes O big of n communication. In one-way case, there's nothing better than Alice sending all of her input to Bob, so the protocol is exponential. And also introduce a partition tree complexity model. In general case, we can query parities of bits at a subset of positions, and we need to compute function. In non-adaptive case, all queries to subsets have to be submitted at once. That means that the following query can depend on previous one. And for example, we can consider majority. There exists an adaptive protocol where where we first query parity of first two bits, and then depending on it, we either query the first bit or the third one, and we can compute the function in two queries. In non-adaptive case, we would have to query all the bits. There exists a relation between these two measures. We consider XOR function f big, which is f small of XOR of its arguments. And for functions defined that way, one-way combination complexity doesn't exceed non-adaptive partition tree complexity of f. Indeed, we have a following protocol. If the tree queries parity over subset S, Alice calculates the parity over her part of input at that positions, sends it to Bob. Bob calculates parity over the same subset of his positions, XOR it with Alice parities, and names and gets the result. And in fact, there is an equality between these two measures for total functions. It was proved by Montanari and Osborne, and proof uses Fourier analysis. For general case, similar upper bound exists. Communication complexity of function f doesn't exceed 2 times parity decision tree complexity of corresponding function. And proof is similar. When tree queries parity of a subset S, Alice queries the same. Alice calculates the parities of same bits of her input X, sends to Bob. Bob calculates parities.
Wait a second. What are you proving now?
What?
So I'm confused a little bit. What are you proving now? Which statement?
The lemma that communication complexity doesn't exceed 2 times partition tree complexity.
In two-way communication model, right?
Yeah, in two-way. So Alice, there is a subset that tree query named S, and Alice calculates parity over her input. Bob calculates parities over his input. They exchange the parities, and now they both can know the parity of X plus Y over that subset, and they know and because of that, they know which set they have to query next. And Hatami proved that, in fact, there is a polynomial lower bound, and proof use Fourier analysis again. And as a corollary, we get that for XOR functions, Lagrange conjecture is true if decision parity tree complexity is polynomially related to logarithm of Fourier sparsity. I told about composition of functions. It works like here on the picture. Here we can...
Wait a bit, because you are talking very fast. Can you switch to the last slide?
Yeah, I'm sorry.
So Lagrange conjecture for XOR function is equivalent to similar conjecture for decision tree complexity, right?
Yeah, for decision tree.
With these XOR queries.
Yeah.
So, and I do not remember. It is so open, I mean, the log-line conjecture for XOR functions.
I'm not sure, but I thought that yes.
Yes, it is. Yes, it is.
So the main your topic is to that log-line conjecture for XOR function, and now you reduced it to that conjecture.
No, it may be an application, maybe like someday, and it's the reason we studied XOR function, but we don't prove a log-rank conjecture.
Yeah, so that's not what this is still a motivation, right? So we just know that
still motivation.
Yeah, this is still about motivation. So it's Hatami and others, they proved that connection, and now we know that to solve the log-rank conjecture for XOR function, you just need to solve something.
But what is this talk about? About decision tree complexity with XOR queries of XOR functions, or what?
About relation of partition tree complexity of XOR functions and communication complexity. So it's communication complexity versus partition tree complexity.
Yeah, so there's
didn't Hatami at all answer that question already?
Answered for total functions, and we tried to solve it for partial functions, but only for one-way case.
Yeah, so so you can observe that there's very total here in this theorem, and yeah, that's the issue.
Both Osborne and Hatami proofs, they use Fourier analysis, and it works only for total functions.
Okay, so it's not very necessary to understand all of this because it's just a motivation.
It's just a motivation.
Okay.
But it is still nice to understand this.
Yeah, nice.
I went too fast. I will try to slow down. Sorry.
And we can still discuss. There are questions.
Okay.
We study composition of functions, and
but wait, what is this? Is this still about the motivation or what? I mean,
yes.
Yes. Okay.
Yes. So basically, what we have just discussed can be viewed as a Lifton result. So we now
it's just what the Lifton result is. We define a composition of Boolean functions, like here with equality and majority. We divide inputs into blocks, apply gadget for each pair of blocks. We get a bit string and apply the second function to that string. That's how the composition of Boolean function works. And Lifton result is a result when we consider some function f that's had in a big model, like decision trees, consider gadget, and for composition, we are trying to prove that it's had in a strong model.
So in this example, the gadget is equality?
Yeah, and we will study XOR. For equality, such result exists for partial functions.
And what do you mean by weak and hard?
Well, I don't think that there is a formal definition, but like I don't think that there is a formal definition, but it's like more flexibility in communication complexity. You can choose.
Hard means of large complexity, I guess.
Yeah.
Yeah. Okay.
And weak means more or less a model in which you know rather well how to prove lower bounds, like decision trees.
So
thank you.
Now the problem. The results on communication complexity versus parity decision tree complexity rely on Fourier analysis, and because of that, they apply only to total functions, and that's not true for a lot of other Lifton results. So we study.
Wait. These results in the first line, they are for XOR functions or for arbitrary functions?
Like for XOR functions, it is not known for total function, for partial functions, And there are other gadgets like equality and disjointness, I think, for which it is known for partial functions also.
So this slide, and I guess that all cover slides are about XOR function, XOR gadget.
Yeah.
So we will talk about only XOR gadgets.
And the problem is if the relation of Montanaro and Hatami about communication complexity versus parity decision tree complexity of XOR functions translate to partial functions. And we mostly study one-way case. The answer is that it depends. We prove that for partial functions, if number of undefined points is bounded with that vector, then the measures are equal. And there are two known things. First is that the number of undefined points is limited. And the second is that the number of undefined points depends on t.
Wait a bit. So here you assume that how capital F is defined from little f.
Capital F takes two Boolean strings as arguments, XORs it, and passes it to little f.
Just bitwise XOR, right?
Just bitwise XOR, yeah.
Okay, so you are given that the complexity, one-way communication complexity is T. And you are given that F is undefined on a small number of points, right?
Yeah.
For example, F is total. For total, this is already known.
For total, yes. That's already known, but we provide as a proof.
But now you assume that it is just small.
Yeah.
And then the communication complexity one way is equal to that, to non-adaptive query complexity. And the equality is just it is. Not big O or whatever, just equality.
Just equality.
Okay. So in one direction it is easier. I mean, the left-hand side is
yeah.
But the claim is also in the right, in the other direction.
Yeah, exactly.
Okay.
So, and the two annoying things. First is that the number of undefined points is limited and that it depends on t, and both of these things are unavoidable because of that separation result. There exists
wait a bit, can we at least a little bit see about that, see that upper bound? So the total number of points is 2 to the n. So now more or less it is 2 to the minus t fraction, if we forget about that square root. So if t is large, for example n, then the function must be almost total.
For exactly n, it's a corner case for which equality holds, but for t n equal to n minus 2, that's a lot of undefined points. And that's a lot of points where function is defined and equality already doesn't hold.
And now you want to explain that you can't strengthen this result. I mean, you write that both are unavoidable.
It probably can be strengthened, but the number of points is still limited and it still have to depend on t. Maybe it can be strengthened a bit, but
for example, you have a counterexample if this upper bound for the number of undefined points, I mean, there is no such upper bound. then it's not true, probably, right?
Yeah, if there's no upper bound, it's not true. Like it's like this. So
Wait, you
we
haven't
find
specified. So there is no guarantee in decision tree or in communication complexity when the function is undefined. So everything can be output by decision tree and communication protocol, right?
for function undefined or no input.
What is the which model you consider for computation of partial function? So the decision.
Yeah, we can answer arbitrarily. So if
So the decision tree has to compute some continuation extension of that function.
Yeah,
to
some extension and same with communication complexity. And there exists a separation. There exists a function on which two measures are not equal. To be more precise, for t equal to some factor of n, the communication complexity can be separated from non-adaptive parity distribution tree complexity with smaller factor of c prime. And for c larger than 1/2, the number of undefined points of that function is limited, and it's limited with the following value, where d is defined that way. And for corner case, for case when c is large, that is non-adaptive parity distribution tree complexity is large. Communication complexity is also large but smaller than c. But d is small, so there's small number of undefined points such that f separation f exists. So we can't. So the factor t is unavoidable because there exists a function with a small factor here for large t.
So why is unavoidable? I mean, the first theorem already claims that it's unavoidable.
First theorem claims that there exists a separation for some number of undefined points, and this statement is that this for large value of non-adaptive parity distribution tree complexity and large value of communication complexity, there exists separation with relatively small number of undefined points. Like d here is small.
But why are you interested in the number of undefined points? It's the number of undefined points. The smaller it is, the stronger is the result.
Yeah, the smaller it is, the stronger is the smaller it is, the stronger is separation. Yeah.
So and you obtain here linear separation, and the number of undefined points is an exponent with again linear exponent, the power with linear exponent.
Right, and this is true only for C at least 1/2, so greater than 1/2. So it's only for large complexity.
I mean
complexity.
The last item, but the
right. But you can. Right. But where you have C is you can see that C is greater than 1/2. So we have this reasonably small number of undefined points only for a rather large complexity, for a rather large decision tree complexity. Should be at least n/2.
And result is even stronger because we can you told about linear separation, we can get exponential separation for function for which non-adaptive parity decision tree complexity is square root of n times log n, and the value of communication complexity is logarithmic. So there exists an exponential gap, but the number of undefined points is large. And this result translates to two-way communication complexity versus adaptive parity decision trees. So there exists no polynomial relation between two measures for partial functions, even for general case. And also we study several extreme cases.
Wait, you are talking too fast.
I'm sorry.
We still have to digest this. So you can obtain you can obtain the separation when the function is almost nowhere defined, right? I mean exponential separation.
Exponential separation, yeah, when function has few points when it's defined.
And why do why they translate to two-way complexity? I mean, it follows from the proof, or
it follows from the proof. This function has only one point when it takes value 1, like the several points when it's equal to 0, and only one point when it's equal to 1. And for such functions, non-adaptive parity decision tree complexity is equal to general parity decision tree complexity. It's the way the function f is built.
So wait,
I think
so
you can also you also have
separation between even
Yeah,
between one-way communication complexity
and
versus
two-way.
versus decision tree complexity, right?
Yeah.
Okay.
So there are also several corner cases we studied for value of communication complexity equal to 1. There may be arbitrary number of undefined points. When it's equal to, we have slightly better bound on number of.
Which line are you explaining now? The first line?
Yeah.
First line.
In first line, there's equality, and it doesn't depend on how many partial points we have. In second line, it's just a bit, we got rid of division on root of n.
Okay. The idea is now to consider only functions as a very small one-way communication complexity. So if it is 1 or 2, then you can claim something which doesn't follow from the previous.
Yeah, something a bit better.
So if it is 1, then it is a non-adaptive Fourier complexity is also 1, whatever function you start. If it is 2, and the function is defined, I mean undefined on at least 1/8 of its inputs. Yeah,
we got rid of division on square root of n.
So we relax this bound about.
Yeah, a bit.
Okay, so then they again coincide. And if it is 7,
yeah, if it's 7, it's the smallest.
Without any upper bound of the number of undefined points, it is at most 8.
It's a separation.
It's a separation.
Yeah, there is a separation. It's the same function, and for that function we can get the separation for the value of computation complexity equal to 7. It's the smallest value for which we got separation.
So maybe the separation exists also for 2, but you don't know still.
Yeah, for 2 we don't know. It may exist. And for large complexity, also we have something a bit better. If it's at least n-1, there is an equality. And if it's n-2, there already is a separation.
And in the large complexity case, there is no upper bound for the number of undefined points at all.
Yeah. Yeah.
So, but you know how many, because you have this example.
Yeah, we have this example. It's like for large computation complexity here, I think that's a small number of undefined points. Like it's n-2, so it must be like d must be near 0. And so here it's a small number of undefined points. And I'm going to show some parts of proofs. Sorry, the computer battery is running low. I'm going to show some parts of the proofs. First, we introduce linear-algebraic framework that's used both for equality and separation results. And it works in a following manner. In one-way communication complexity, Alice sends a message to Bob, and then Bob names the answer. So we can say that Alice computes some total function h of her input, sends the value to Bob, and then Bob computes function of 2 arguments. First is the Alice message, and second is Bob input. And if function is defined on the input, then the answer Bob computed must be equal to the function. We introduce a good shifts. Good shifts are just vectors such that there are 2 points, and XOR of these points is that shift, and the function h has the same value on these 2 points. And we can notice the following thing. Let there be 2 points A and B, and f is defined on these 2 points, and h is equal on these 2 points. In that case, f on these points is also equal. That's because Bob has to answer correctly, so these equalities hold, and this equality hold because h of A is equal to h of B. So these 2 values are equal, but only if f is defined on points A and B. And we can make a little bit better. We can substitute C as a second argument here. So here the equality is again equal because Bob the value of this function must be equal to f because of this. And this equality holds because h of A is equal to h of B. And because of that, we got that if f is defined on a plus c and b plus c, and h is equal for a and b, then function f for a plus c and b plus c is also equal. And we know that a plus b is, in that case, we call a plus b a good shift. And we can reformulate the previous lemma that if the 2 points u and v such that u plus v is a good shift, then f on these points is equal. That because here because u plus v is a good shift, it means that the 2 points a and b such that the XOR is a good such that the XOR is equal to u plus v and h is equal on these 2 points. So we can find such 2 points a and b and such c that u is equal to a plus c and v is equal to b plus c. And because of that, if u plus v is a good shift, then f must be equal for these 2 points. So are there any questions here?
No.
Great. So we can then we introduce a total H-induced graph. That's a graph where we connect two vertices if the XOR between these two vertices is a good shift. Like here on the picture, function H is defined the following way, and there are 3 good shifts between two A's, between two B's, and between two C's. And we consider, and these 3 shifts generate the total H-induced graph, which is a cube, because we can draw this edge from this vertex, from this vertex, from this vertex. We can draw vertical edge from all the vertices. And same for edges looking forward, and same for horizontal edges. That way we draw all the edges. And
but this is already not clear. You have defined a good shift, but what are you illustrating now? Why this brown H is a good shift?
they are like they're good shifts because that's a shift between two vertices with the same value. So good shift is not an edge. Good shift is a XOR of these two vertices. Yeah, it's technically it's not an edge.
So you indicated these letters on the Boolean cube are the values of H. So
yeah.
what sense D, B, or C, or E, or A? And you just indicated all the good shifts by
yeah.
edges. Okay.
And there are 3 good shifts, but they generate all the edges of the cube. Because
what do we allow with these 2 shifts? To add them?
What it allows to...
I mean, in which sense they generate all the edges of the Boolean cube?
Like
you can say it in the following way. On the left we have this H and we have this orange or brown edges, and on the right, so we define this graph G sub H, and what we do, we take all these brown edges and we draw all edges that are parallel to them. That's what we do. And why do we do this? Because on the previous slide we showed that f should be equal. If we connect something by an edge on the right, then it means that the value of f is equal between this point at this point.
So I have another example here. That's other way to define H. And here we have these good shifts, and we draw all the edges parallel to them, and we get like 2 clicks like here. So here is a total H-induced graph for such H. And if points are connected with an H, then they have the same value of F. Now we throw all the points where function is not defined. We take the total H-induced graph, that's the first picture again, and it was a cube, and here function is undefined on these 2 vertices. And we throw these vertices off, like it was this vertex and this vertex, and we remove that, and here what we got left. And for partial graph, if 2 vertices are connected, they are F is defined on these 2 vertices, and there's a good shift between these 2 vertices. So F must have the same value on 2 vertices if they are connected in partial H-induced graph. And so we have the following lemma. If 2 vertices are in the same connected component of partial H-induced graph, then they have the same value of F because of transitivity. And in other words, if A is connected component, that function restricted to that component is constant. So for such choice of edges, function will be just constant on the whole cube. And the lemma works in converse direction as well. Like here we had that if there is a communication protocol, then A is constant on all the connected components of partial H-induced graph. And here we prove the converse statement. If for some function H, we have found some F which is constant on each connected component of partial H-induced graph, then Bob can compute the output. And for 2 points x and x prime, you have that value of H on these points is equal, then for each y such that F is defined on this XORs, the value of F is equal. That follows from the definition of partial H-induced graph. If F is defined on these points, and here x and x plus x prime is a good shift, and that means that these 2 points must be connected in partial H-induced graph, and because of statement of the lemma, that means that these values must be equal. Bob gets from Alice some string alpha, which is computed as h of x, and then Bob can find some x prime in the pre-image of alpha. And he selects such x prime that F is defined on this value, if he can. And if he can find such x prime, he answers F from x prime plus y, otherwise he answers arbitrarily. And then we notice that the thing that Bob answered, F of x prime plus y, is equal to F of x plus y. So Bob computed the required value, knowing only Alice's message and Bob's input.
Okay, so again, wait a second.
Sure.
You have just reformulated communication complexity of XOR functions in terms of some characteristics of function f. I mean, you're interested in the one-way communication complexity of capital F. And
Yeah.
now you reformulated that in terms of some combinatorial characteristic of function f, right?
Yeah.
Little f. Then
Yeah.
you repeat it once more. I mean,
Sure.
without any proof. Just say it again. What is this characteristics? So you consider Boolean Q.
Yeah.
And you say that the function must be constant on certain subsets. So which are those subsets? Say it again once more.
We draw an edge between two vertices if the XOR is a good shift. And
say it again. What is a good shift?
Yeah. We name a vector a good shift if it is a XOR between two points on which h has the same value. So here h has value a on these 2 points.
Which are those values? These are values of the function little f, right?
No,
Little
it's
a,
value
little
of
h.
function h, little h.
But you have no h. I am confused a little bit. Do we have a h in advance or not?
It's I understand the problem.
Sorry. A communication, one-way communication is small if there is a function h.
Yeah, in direct direction, we get h from communication complexity. In converse direction, we say that if exists
for some
h, yeah, if for some h.
Okay. Then the combinatorial characteristics is as follows. There is some h, some function h.
Yeah.
We consider for which, then we consider all good shifts.
Yeah.
And then we consider some graph. Say it again, which graph it is.
We draw an edge between two vertices if XOR of these vertices is a good shift.
Okay.
So, and then we remove all the points where function is not defined.
Okay.
And the function must have the same value on each connected component of resulting graph.
And the graph consists of all edges parallel to good shifts.
Yeah.
Okay, so you reformulate it in this way. Still, there is it's a hard combinatorial characteristic because you need to look through all the h functions. Okay.
For separation, we have to define the h some way, and then to find f for that h. That's how the separation works. We find some h, then we find f for that h. And in indirect case, h is given because of the protocol. And for decision tree complexity, we also make some characterization. If non-adaptive parity decision tree complexity is equal to t, then there exists a linear subspace with dimension at least n minus t, such that for any coset of that subspace, f is constant on that coset. So, like here we queried first 2 bits, and we found the coset of dimension 1 such that f is constant on all of the vectors in the same coset, because we queried only first 2 vectors, so f can depend on the third vector. And the proof is following. If the value of non-adaptive parity decision tree complexity is t, then the t queries, and we can represent a query for parity with an inner product. So we wrote all the queries into rows of matrix S, and then this multiple is just the answer on all the queries. And it defines function f. And we define subspace L to be subspace of all vectors such that S multiplied by X is equal to 0. And because of that, on each coset of L, S times X will be same. And because S times X is the same, then F of X must also be the same if it is defined. That's the other picture. Here, the query is parity of all 3 bits, and it induces the following subspace. So orange points is the subspace, blue points is the coset of that subspace. And the dimension is correct. And we can see that here all the either 0 ones or 2 ones, and the parity is 0. Here the parity is 1. Now I'm going to prove to give some ideas of proof for equality results. The plan is following. We suppose that the value of communication complexity is t. We consider corresponding function h. And the next step is like all the other steps follow from the framework. Here is what we are going to prove. We're going to prove that there is a subspace of a large enough dimension such that partial h-induced graph, when restricted to coset of that to any coset of that subspace, is connected. Because partial h-induced graph is connected on each coset, that means that f is constant on each coset. And because of that, it follows that non-adaptive parity decision tree complexity doesn't exceed t. And then equality holds. So this
wait.
Yeah.
You say that you need to prove this second item, right?
Yeah, we need to prove second item.
There is a large subspace, I mean of large dimension.
Yeah.
Actually, you know that the dimension can't be larger than n minus t.
Yeah, it can be larger than n minus t, and we need to prove that there exists subspace of dimension n minus t.
Exactly n minus t. So that component
For each
what
coset,
is written here, g of
for
hf is
partial h-induced graph, and we restrict it to all the cosets. We take all the cosets of L, restrict G to each coset, and each restriction must be connected.
and why we need that it is connected? Say it again.
Because if it's connected, then f is constant, because f is constant on connected components of partial. F is constant, and if f is constant, then we can get this.
Decision tree complexity is small. You just explained it on the previous slide.
Yeah, it's in that here we know that communication complexity is small, and we use it to say that because of that, we have a partial H-induced graph such that we can find such L. So it's not that cache complexity is small because L exists. It's that because cache complexity is small, such L will exist. And there are two cases. We suppose that implication complexity is equal to T, and we consider the partition. Each class of the partition is a pre-image of some vector. So H is all the pre-images of function H. Like on each class of H, function H takes the same value. And because of that, each vector between 2 points in the same class is a good shift, because on these 2 points, H small has the same value. And the first case is when H corresponds to cosets of L with the dimension we need. In that case, like here, function is defined, function H is defined like this. The partition is into 2 classes, and good shifts are all these edges. And that's how total H-induced graph looks, and connected components of it are cosets of L. And F is constant on each of cosets because they are connected. And because of that, we have the required bound. So we said that good shifts are vectors in our space, all the vectors in our space. And we draw all edges parallel to good shifts. And we'll get all edges inside cosets drawn. And because of that, we will get cliques corresponding to cosets. And the second case is more difficult. Here, H doesn't correspond to cosets of any L. And in that case, we say that some class of H will intersect 2 cosets of L. Because that 2 to the power of n cosets and in H and in H the maximum 2 to the power n minus t cosets, and in H the maximum 2 to the power of n minus t classes. Because function H is, because we have it's not n minus t. I made a mistake.
Classes. I mean, H has 2 to the t classes.
Yeah, H has 2 to the t classes, and the 2 to the t cosets. I made a mistake. 2 to the t classes, 2 to the t cosets. And because of that, there is, and they don't coincide. So there must be a class that intersects at least 2 cosets. And if such class exists, there are 2 points with same value of h, but lying in different cosets. And we can select the space L of that dimension in any way. And because of that, there is a good shift outside of any space L. For example, here h takes either value 0 or 1, so it's so t is equal to 1, and the graph is following. So here is zeros, here is ones, and good shifts are all the orange edges, and there is, like here I selected subspace and drawn it with points, but you can see that any way, however we select the subspace, there will always some edge outside of that subspace. And we use that observation to get that there are n minus 1 minus t plus 1 linearly independent good shifts. There is, for each subspace, there is a shift outside of this subspace. And suppose we have only n minus t linearly independent shifts. Then we take a subspace which contains all of these shifts, and there exists some shift outside of that space. And that means that we found n minus t plus 1 shifts. And now we do the following thing. We have n minus t plus 1 shifts, and we can find an embedding from Hamming cube. So we have a Hamming cube. We have Hamming cube, and we have some graph, but there, from each vertex, there are linearly independent shifts S1, S n minus t plus 1. So here is S1, S2, S3, and there are such vertices from such edges from each vertex. And then we build an embedding of that Boolean cube into that graph. We map, like we map some vertex to some other vertex, and then we have that edge and we map it to S1 and so on. So we got an embedding from Boolean cube to a coset, and Boolean cube is connected, so we have that we have that the coset is connected because of that Boolean cube. To be more formal, the mapping will work in the following way. We have vertices of a cube, and we take some vertex of the coset, let it be vertex alpha, and then mapping works in the following way. We take vertex v, we multiply it with the matrix S1 S n minus t plus 1, and then we add alpha. And so zero vertex will get like here is alpha, so this vertex will get here, then here is an edge, and it will get here, and so on. So here from each vertex we have edges parallel to S1 to Sn minus t plus 1, and all of these edges will be mapped to these edges from each vertex. And because of that, we can say that the coset is connected. And so for total functions, this inequality holds. For partial functions, we
But wait,
do.
what was our goal? Our goal was to prove that two quantities coincide, right?
Yeah.
But you obtain just a contradiction, I see.
Yeah, that's a contradiction. So it's impossible. That second case is impossible.
So in the first case, we have what we want, but in the second case...
in first case, we have...
you should say in advance that you want to prove that the second case is impossible, actually. Okay.
Yeah, I should have done that. So in case of partial functions, we do the similar way.
But what we want to prove now for partial functions?
That was the equality for total functions between measures, and we want to prove equality for partial functions.
With some additional requirements.
Yeah, the theorem is on the bottom of the slide. So
I see.
And Dmitry, you actually have about less than 10 minutes now. And
yeah, so I have to review separation results. So what we have to do here.
Dmitry, you should have in mind that now we can understand only simple things. So have you some example which can be presented in a clear way using pictures or whatever? I mean, when you separate.
Think of an example of a function is very simple. So
Okay.
I have a picture for separation. We build the separating functions like this. So that's a 4-dimensional Boolean cube. And function is equal to 1 for the string of all ones. And it's equal to 0 for strings having small having white. Having in white at most k. So here the blue strings are zeros, the orange one is 1. And for such function, non-adaptive parity complexity is equal to ordinary parity tree complexity and is equal to k plus 1. We show it by contradiction, and we want to define.
Maybe this is just a thing we can understand. I mean, why? Because usually it's easy to understand. So the decision tree complexity, this parity queries. So do you need actually parity queries or just normal decision tree complexity?
Yeah,
Well, the upper bound is just normal, yeah.
It's just normal because
You can switch to the previous slide because it's written there. Yeah.
Yeah,
here
we can get the answer in k+1 queries. And it's all ordinary queries to bits. And in the opposite direction,
But how do you know which
yeah.
variables to query?
We can query any single k+1 bits, because if that's a if we are given a string of ones, yeah, all will be ones, and otherwise some of them will be equal to 0.
Okay.
And in opposite direction, we assume that parity decision tree complexity is doesn't exceed k for contradiction, and we consider some input, and we consider string of ones as input, and there will be some set of queries, and for such set of queries, and we again write queries into rows of the matrix, and matrix has k rows and n columns, and from that notation we can see that that we can consider the space of columns of matrix S, and this and A will lay in that space. But rank of matrix S is at most k, so dimension of that space is most k, so we can throw off n minus k vectors. And because of that, A can be represented as a sum of some k vectors. And because of that, we can replace x with some y having at most k ones.
Okay.
And to construct H, we want here the distance between ones and zeros is large. It's equal to n minus k. And we want good shifts. We want values of H.
We want to show now that the communication complexity is small.
Yeah. And to do
right,
so,
we want to show. Yeah, you can say this. Just to remind people of that, right? So you need to show the communication complexity is small, so we need to construct some H function, and we prove that if H is not equal to on inputs on which our function outputs different values, then we are fine, right? So that's what
So the idea is that we want H to be equal only if the points is near, and the idea is covering codes. Covering code is a set of Boolean strings such that for some R, the distance from any Boolean string to some string inside the code doesn't exceed R. So we can draw balls of radius R over each string C, and these balls will cover the whole space, the whole Boolean cube. And there exists some bounds on the values of K and R that allow us to build the code with
So we
parameters
consider,
to
so
define
to
this.
say, optimal covering course, and how do we define H then?
Yeah, we define H to like covering codes give us balls of radius r, and some point may lay in several balls, but we say that H will be the one of the balls point lays in. So
Some
the
ball containing that
yeah, some ball containing that point.
point. Okay.
And because of that, distance between 2 points of H will be small. It won't exceed 2 times A, because from X to C it's A, and from C to Y it's A. And here is an example. We here drew edges between all points at having distance at most 2. And here, orange part isn't connected with the blue part. And that's the example that if a code with such parameters exists, then distance between 2 points in H is then the distance is at most n minus k minus 1, and distance between zeros and ones is n minus k, and because of that, these 2 points are disconnected.
But can you explain this just in communication protocol terms? So Alice sends Bob
Yeah,
the ball.
ball.
What then does Bob?
Alice sends Bob the ball, and Bob.
Yeah, I think it's not hard to say. So Bob shifts this ball according to y, right? So if you consider this function capital F, then you take an input of Alice and you store it with an input of Bob. So what Bob will do, so what Bob knows, right? It knows that X is inside of the ball.
Yes.
So if using that, Bob can shift this ball by y, and then he will know that x plus y is inside of some ball and he knows this ball.
Yes.
And now we can observe that this ball cannot intersect both points where we output zeros and both points
because
where
they
we
are
output
far
y.
enough.
Too far away.
No.
Yeah.
All orange points are far from all blue points, and that's it.
Yes. Yeah. So your ball can touch only orange points or only blue points, and then you know that the output is there. That's it. Yeah.
It's very clever.
Yeah, it's nice, but in the end of the talk you can understand something.
Yes.
Yeah. So here's the table of all the results on separation.
All your results on separations are here.
Not all the corner cases was in previous slides. Here is for general case. I think that's it.
Okay, thank you.
Thank you. I'm sorry I was too Russian.
So are there any other questions to Dmitry? I guess not. Okay. Thank you anyway.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Now
Bye.
we can leave. Okay.
Goodbye, everyone.
Bye.